So first we will continue chapter 7. Okay. We will go over the second part, which deals with the solidification time. So we have already defined together the solidification time as the total time required for casting to solidify after pouring. And we can see this in the following graph. So if you consider a pure metal, for example, then we consider that we have two phases for total solidification time. The first phase is liquid cooling, and the second phase is the local solidification time, which corresponds to change of phase from 100% liquid to 100% solid. And in case of an alloy, okay, in case of alloy, also it's the same definition. It's from end of pouring to complete solidification. But just the difference here is that the change of a phase will occur in a range of temperatures because as we have seen together in the course material, that when we have a mixture of two phases, then we have a range of temperatures for which melting will occur. This is why during the change of phase, in case of an alloy, I don't have a constant temperature, melting temperature, but the temperature will still vary during the cooling process. Okay, but freezing begins when we have the contact line between the vertical line corresponding to the percentage of composition and with the liquidus line. So here we can find the temperature at which we will have beginning of freezing, and the final temperature is determined by the intersection with the solidus line. So we get a range of temperatures for which change of phase will occur from 100% liquid to 100% solid. And but the definition of total solidification for both is the same. It is from end of pouring until complete solidification. Okay, so here now what you will learn to do is how to compute the solidification time. Okay, now the solidification time is determined experimentally, and it is function of the mold constant and the volume to area ratio, surface area of casting. We have that the mold constant will be, as we will see together, function of several properties, but not concerning geometries of the pattern. So the mold constant will be function of the material of the mold, the material of the casting, and the pouring temperature of the metal of the material. Okay, while the second factor affecting the solidification time is related to the geometry of the pattern and is calculated as the ratio of volume to surface area of the casting to the power n. Now, what do we mean by volume over surface area? The surface area is the contact area between the final cast that will be produced, okay, and the mold. So you know that the mold has external and internal surfaces. So for example, if I want to cast a cylinder with a certain hole inside, okay, what will be the total contact between the molten metal and the cavity? You will have external surfaces and you will have internal surfaces. Okay, so in this case, the total surface of contact will be the external surface plus the internal surface. So in this example, if you want to calculate if you want the surface area of casting, it will be equal to, if I call this as the outer diameter, and this is the inner diameter, and let's say they gave us the length L. So we have L, we have the outer, and we have the inner. Then we can say that the total surface area is pi times d outer, which this would give us a perimeter of the circle. And then we multiply by what? We multiply by the length. So in this way, we get the outer surface area. Now for the internal surface area, we should add plus pi d inner times L. And concerning the volume is, since we have a hole, then for the volume it's pi d outer square over 4 minus pi d inner square over 4. Okay, so this is how I can find the A and V, and the total solidification time will be proportional to the ratio of V over A. So why? If we can think about it, why if V over A is higher, the solidification time will be higher? Because look, higher the volume to solidify, of course, higher will be the solidification time. Now, why if I decrease the contact area, the solidification time will increase? Because heat transfer between the external walls and the core with the metal in the main cavity, the heat transfer will take place through the surface of contact. So smaller is this contact surface, slower will be the solidification process. So if you want to decrease the time of solidification, you should increase the contact area and reduce the volume. While if you want to increase the solidification time, then you should increase the volume and decrease the area. And of course, another strategy for increasing the solidification time is to play with the mole constant. Now we will see why it's very important to study well the solidification time, because we will see after how it will affect the solidification in the main cavity. Now, as we said, this formula is empirical. Yes. Yes. Who was asking? Look, I cannot hear you. If you want, type your question in the chat. So this is an empirical relation between solidification time, mole constant, and volume to area ratio. Now, since it's experimental, then in general, Cm and N are found experimentally. Now, for N in general, it's typically equal to 2. And for the mole constant, it will be provided, or we can ask for it if they gave us all required information. Now, what are the factors that will affect the mole constant? First, just I will want to tell you that this is called the Shvorinov's rule. Okay, it is the name of the scientist who comes with it. So it's Shvorinov's rule. Now, this rule is very important. We'll see why. In order to determine the mole constant, we should know several properties. So Cm is mainly affected by the mold material, the thermal properties of the casting metal, and the pouring temperature relative to melting point. As you can see, the geometry of the pattern will not affect the value of the mold constant. This is why if we have done experiment under the same conditions, and if we use a certain mold material with same thermal properties of casting metal and same pouring temperature, we can use the same value of Cm even if we change the geometry of the pattern. So values of Cm for a given casting operation can be based on experimental data from previous operations carried out using same mold material, same metal, and pouring temperature, even though the shape of the part may be quite different, because the shape will affect the ratio V over A, but will not affect the value of the mold constant Cm. Okay, so if you keep these conditions, you can use the same value of the mold constant. Now, what Vorinov's rule tell us? So what are the conclusions we can make from this rule? First, a casting with a higher volume to surface area ratio cools and solidifies more slowly than one with a lower ratio. And this is what we talked about. Now, how we can use these properties? It will help us in designing the riser. Why? In order to feed molten metal to the main cavity, the solidification time for the riser must be greater than the solidification time for main casting. Why? Because if we look back to the definition of the riser, so if you go back to the figure representing the different elements of our casting process, as you can see here, we have talked together about functions of the riser, and I will repeat here in brief what we talked already about. So whenever you want to do a casting operation, the first step is to pour your metal, okay, to reach your main cavity through the down screw and the run. But you know that when you introduce your molten metal, you might have some gases that will enter with it. And if not escaped appropriately, they will lead to formation of pores in the final casting product. This is why one of the objective of riser is to escape these gases. How? After the pouring process is over, okay, the riser will allow you to continue to supply molten metal to the main cavity. And in this way, it will help into escaping these gases by taking their place. So the first function of the riser is to avoid formation of voids due to gases which are introduced during the pouring process. Another important function is that during solidification, we will have what is called shrinkage. Shrinkage is mainly due to a reduction of volume because of increase in density. So when you cool, density is increased. This will, and since you have the same mass, then the volume will decrease. In order to compensate for this effect, and in order to not have large variation between the pattern size and the final casting size, the riser will continue to supply molten metal during solidification process in order to compensate for shrinkage effects. In this way, at the final state, the deviation between cavity, if you want cavity design measurements and final casting measurements, you will not have a high deviation if you put the riser in an appropriate way, of course. Now, why we talk about the design of riser concerning solidification time? Because look, in order for the riser to continue to work, it should not solidify before the main cavity. So it should solidify at the end of the process after the main cavity, because it should continue to supply molten metal until the solidification is complete in the main cavity. And in order to ensure this, you have a condition. You should have that the total solidification time of the riser should be higher than the total solidification time of the main cavity, okay? Because it should be able to continue to supply molten metal until the solidification process in the main cavity is over. In addition, this is not the only condition also. Also, we try to have zones close to the riser with higher solidification time. Why? Because look, imagine that, for example, this zone of the cavity will have a smaller solidification time than this zone. What will happen? Once this zone will solidify, because it has a smaller solidification time, it will block the passage of molten metal from the riser towards other zones. This is why what we try to do, we try to put the riser close to zones of high solidification time and far from zone of low solidification time. Because if we put it in this way, then we will not have a blocking effect. So first, the molten metal can reach the far zones for which the solidification time is smaller. And then solidification will start from far zones towards closest zone to the riser. In this way, this is called directional solidification, and we will talk about it. In this way, we will ensure that molten metal can still continue to be supplied to the main cavity until the end of the solidification process. Okay? Now, sometimes it might be complex if the geometry is very complex. So we do several strategies. One possibility is to put several risers instead of one. Okay, and you will see another possibility is to add external chills, as you will see after, which will reduce the time of solidification of zones that are far from the riser. We'll see this in detail in this session. Okay, any
Okay.
question on this?
Yes.
Yeah.
Which area do we consider when we want to take the volume to area ratio?
Okay, look, the area is the surface, is the area of contact between your, if you want, the cavity and your mold. So here, for example, let's say you are interested in this part here, this part. You want to find the solidification time of this part. So what you do is that you consider what is the volume of this part, and the surface of contact is this one. So you have, this is the surface of contact with the mold, and this is the volume, the corresponding volume. So sometimes if I don't have a uniform geometry, for example, if you consider a cylinder, for example, this is a simple geometry. A cylinder will have one volume to surface. So if you consider here, for example, so in general, for a cylinder, it's a uniform geometrical shape. I calculate V over A. I consider the total volume, and I divide by the lateral surface, okay? Because you have contact here, and you have contact here. So you should add all lateral surfaces, okay? And you calculate then V over A. Now, sometimes if you have several different geometries in one pattern, then you should calculate the total solidification time for each part separately in order to see what are zones of high solidification time and what are zones of low solidification time. Okay, so here, for example, in this pattern, you have variable solidification times, which complicate things. But if you have uniform shape, you just calculate one solidification. And you can also take one in average, but it will not be a good representation. And if you can take the whole solidification time by considering, if you want, for the whole shape, what is the total volume over the total contact area. So here's the total contact area is this one, like this, like this. So you should account for this whole area. Okay, of course, if I consider constant depth, I multiply the perimeter by the depth. Okay. Okay. Now,
Doctor?
yes.
You said something about shrinkage, about the density. Can you repeat it?
Yes, I will repeat it in detail now. But what is the idea? When you solidify, when you cool, the decrease in temperature will lead to an increase in density. Okay, and when density increases for the same mass, what will happen? Volume will be reduced. Okay, so dimensions will shrink. This is why we call shrinkage. Dimensions will be reduced. This is called shrinkage effect. This will lead to deviations between the pattern, and you expect this anyway. You expect this, but you can reduce this effect by the presence of the riser, because the riser will continue to supply molten metal to these zones, which will reduce the effect of shrinkage. Okay, so you can reduce the variation between pattern size and final size.
Okay,
we'll see this in more details now. Okay, so if we go back to our slide about riser design, then we will deduce that the riser should have the highest solidification time in order to operate until the end of solidification. Now, since mold constants of riser and casting will be equal, of course, why? Because the riser and casting are characterized by same mold material, same metal casting material, and same pouring temperature. So they will have the same mold constant. But what can differ them in terms of solidification time? The second factor, which is the volume to area ratio. This is why when designing the riser, we try to have its volume to area ratio higher than the volume to area ratio of the main cavity. And this will lead to solidification of the main cavity before solidification of the molten metal in the riser. And this will minimize the effect of shrinkage, and also it will lead to escape of gases, so it will allow to avoid the presence of voids in the final casting probe. Now, let us talk in detail about shrinkage. So shrinkage will take place whenever we cool our metal. Okay, so first, at the starting level of molten metal after pouring, as you can see, at the first stage, you have complete liquid. So you had 100% liquid at the first step. Okay, what will happen just directly after pouring? You will have contact between the relatively cool walls of the mold and your metal. So you will have a very high drop in temperature near the walls, because you will have heat transfer from the molten metal at walls towards the envelope, which is the mold. Okay, and due to this heat transfer, you will have formation of a thin solid layer, because this will cool in a much rapid way, higher, it will cool faster than the remaining part, because due to heat transfer with walls. Okay, so you will have a formation of a thin layer of solid. So already this will lead to a volume reduction, because you know that the density of a solid is higher than the density of the liquid. Plus that when you cool your liquid, also as you cool your liquid, you have also reduction in volume, because density is increasing. So this is called, okay, this is called a liquid shrink contraction. Okay, so you will have reduction in level of the liquid due to, first, the formation of a solid layer at the walls, and due to increase of density of the liquid itself. Okay, so this part is called liquid contraction, which is, or liquid shrinking. Okay, and in general, liquid shrinking takes place along a vertical direction. Why? Because in general, what we do when we have a riser, the riser will maintain supply of, if you want, molten metal to the base in a way to cover the whole base. So in general, when we talk about liquid contraction, it will be in one dimension. It will be perpendicular to the base. Okay. In case not, it will be very clear in the given. So I will tell you that the contraction is along the height, or it will be along the three dimensions. It will be specified in the given. But in general, the first phase of contraction will be along the height, because as I told you, the riser will ensure to have to supply to the base metal to avoid, if you want, shrinkage. And even you know that in general, a liquid is tend to fill the reservoir completely. Okay, so due to this behavior of liquid to fill the reservoir, it will avoid, if you want, shrinkage in direction perpendicular, parallel to the base. So shrinkage will only be in direction that is perpendicular to the base. While once we reach complete solidification and we continue to cool our solid, okay, so once you have complete solidification, now when the solid will cool more, what will happen is the density will further increase, and then you will have what is called solid thermal contraction, because you know that the solid is not like a fluid. The fluid tends to fill due to its property, okay, due to fluidity, it will tend to fill the base of the reservoir, while it will shrink in height. Okay, and in this case, once you reach the complete solid state, the solid behavior is different than liquid, because you know that due to viscous effects, and in fluid you have a viscosity. Okay, in solid, viscosity is infinite, so you will not, solid will not tend to fill the reservoir. This is why when it will contract in three dimensions. It will contract in height, and also it will contract in the dimension of the base. Okay, so in this case, we say that solid contraction is three-dimensional, and this is why we call it a linear thermal contraction. So this is why, in general, for liquid contraction, we talk about just shrinkage in height, while in solid thermal contraction, we talk about linear shrinkage in the three dimensions. So we have a reduction in height and formation of shrinkage cavity caused by solidification first, and then further reduction in volume is due to thermal contraction during the cooling of the solid metal. Now, as you can see here, during the cooling process, we will have formation of shrinkage cavity due to the shrinkage effect. Now, whenever you have a riser, the riser will reduce a lot this effect. So when you place appropriately your riser, you can lead to a closure of this cavity. Okay, so the presence of riser is very important. But here, as you can see, if you are in the case of open molds, in general, in open molds, we don't have a riser. We have a riser in closed molds. So this is one of the advantages of open molds, that we can have the formation of shrinkage cavities. Okay. Now, concerning solidification shrinkage, it will occur nearly in all metals because the solid phase has a higher density than the liquid phase. Thus, solidification causes a reduction in volume per unit weight of metal. We have an exception for this, which is cast iron with high C content. So this is graphite, okay? And in general, it is a good strategy to use graphite in casting because we will reduce the shrinkage effect. So what we can do the graphitization process during final stages of freezing, which can cause expansion that counteracts volumetric decrease associated with phase change. So graphite is characterized by, if you want expansion when cooling, this is an exception. This is why we say that if we do graphitization during the final stage, this means that we add the content in carbon. This will lead to a reduction of shrinkage effect. Okay. Now, what about shrinkage allowance? So you know that even if you have a riser, so the riser can compensate shrinkage whenever I have not reached yet complete solidification. But once I have complete solidification, the cooling of the solid, okay, will lead to linear contraction. So at the end, I will have final shrinkage. This is why we talk about shrinkage allowance. Since we are expecting to have this shrinkage, this is why we oversize the pattern, because when oversizing the pattern, after shrinkage, we can reach the desired measurements. So in general, pattern makers correct for solidification shrinkage and thermal contraction by making the mold cavity oversized. And shrinkage allowance represents the amount by which mold is made larger relative to final casting size. And this is called pattern shrinkage allowance. Casting dimensions are expressed linearly, so allowances are applied accordingly. So the allowance is per unit length, we express it. Now, what about directional solidification? So as we have seen, solidification will depend on the time of solidification. So we try to have zones of low solidification time far from the riser and zones of high solidification time close from the riser. So to minimize effects of shrinkage, it is desirable for regions of the casting most distance from the liquid metal supply, which is the riser, to freeze first and for solidification to progress from these regions towards the risers. Thus, molten metal is continually available from risers to prevent shrinkage voids, and the term directional solidification describes this aspect of freezing and methods by which it is controlled. So let us go back to the figure to explain what we mean by this. So as we said, we try, when we put the riser, we try to keep it close to zones of high solidification time, because this will allow that these zones will solidify at the end, before the zones that are far from riser. So here, when we put the location of the riser, we study the solidification times for the different parts. As we said, if we don't have uniform geometries, then we might have variable solidification times in different regions. So here, for example, the solidification time here is higher because the volume to area ratio is higher. Okay, so what will happen in this way, when you put the riser close to this region, the molten metal can be supplied first to far zones. They will solidify. So solidification will start from here, okay, and will continue in a directional way from far zone towards close zone to the riser. This will allow a good operation because molten metal can continue to reach these zones until the end. On the other hand, if you put your riser here, it will not be a good choice, because if you put your riser here, then first this region will solidify and it will block the passage of molten metal towards the other zone. Okay. Now, sometimes in case of very complex geometries, we might need several risers. Okay. So for example, if you have this, let's say your pattern is continuing in this way, like this, for example. So what will happen? You will have here a zone of high solidification time, and here a zone of low solidification time. So this zone will block first, and a molten metal will not be able to reach this zone. So here, of course, I need two risers, one from this side and one from this side, for example. Okay? Any question on this? Okay. So this is called directional solidification. Okay. Now, in order to achieve directional solidification, we use the Shrobinov's rule to design the casting, its orientation in the mold, and the riser system that feeds it. We locate sections of the casting with lower V over A ratios away from riser, so freezing occurs first in these regions, and the liquid metal supply for the rest of the casting remains open. Another strategies is to add chills. Chills, as their name indicate, have cooling purpose. So we will put them in zones that are far from the riser to have faster solidification. So they are internal or external heat sinks that cause rapid freezing in certain regions of the casting. So let us consider an example. So here, for example, okay, let's say your riser is far away from these regions. Here, the riser is at this location, for example, and you want to, or sometimes if you have open molds, for example, if you have open molds, let's say you don't have the option to use the riser, you can use external chills. So the idea of external chills is to put them in regions that are critical in solidification. So here, because they are far from riser location, they might, we need to cool them in a fast way. To cool them in a fast way, we put chills, external chills, and the cooling effect will lead to heat transfer from the metal here at the proximity of the corner towards the external chills. In this way, this region will solidify faster, and then because this region is far from the riser, we desire it to solidify in a faster way. So this will allow us to minimize the possibility of formation of voids, because here, as you can see, you have the possibility of void formation at these zones because they are far from the riser. So by putting external chills, you will minimize the effect. Okay, instead of having a big shrinkage cavity, you will reduce the size of the shrinkage cavity. So if you don't have external chills, you will end up with a certain shrinkage cavity, while by the presence of the external chill, you can avoid this. Okay. Now, for the riser design, we know that at the end, the riser metal that will remain is a waste. So we can reuse it if we remelt the casting. But in order to reduce the waste and the need to remelt, what we can do, when we do the design, we just try to minimize the volume while maximizing the ratio V over A. Okay? So riser is waste metal that is separated from the casting at the end and remelted to make more casting. So when you finish your process, if you have a remaining part in the riser, you will trim it, okay? You will separate it from your final casting. This is why when you design it, you try to minimize the remaining quantity by appropriate design. So to minimize waste in the unit operation, it is desired for the volume of metal in the riser to be minimum. But also, we should compromise this with the other factor that the volume to area ratio should be maximum. So the geometry of the riser will play a big role in its in selection, okay? Because we will try to select the geometry that will lead to minimal volume while resulting in higher V over A, okay? This will allow the riser volume to be reduced to the minimum possible value. And we will see this together in problems. This is for the material of chapter 7. Now we will start together with problems. So if you don't have any question on the material, I will open a new session. Any question before I open the new problem session? Okay. So yeah, I will open a new session.